Okay. Whether my slides are visible to you? I am audible.
Yes, sir.
Okay. So last class we discussed about that virtual memory protection. In that, what way the basic paging as well as segmentation will be helpful. What are the 6 parameters in that we have discussed, and then we discuss about what how that protection mechanism will be effective. All those things we have discussed. So what way that virtual memory will be useful for in order to increase the performance of the processor, all those things we have discussed. How that virtual memory address is converted into physical address also we have discussed. So just in order to quickly recall that one, why? Because this is also used in this particular topic. So that's why again in that book chapter it is recalled, so that information and all briefly they are given. So protection as well as instruction set architecture. So virtual machine. So basically, it will have some emulation methods that provide standard software interface. So what will be the emulation method? Anyone can tell me? So there will be something called as standard software interface, that is going to be virtual machine monitor, which will be used. Okay, so already you all know, even though there will be that the basic instruction architecture is going to be same or otherwise it is different, so we can use virtual machine. That important. So whether that operating system is going to be same, or otherwise whether we are following that instruction architecture is same or both are different, there is a possibility for migration is possible. So just now that's why I told you, nowadays that application people are using Docker container. So there will be some images, whatever application you want, you can convert it as an image, and then that is going to be implemented. Whatever requirement required, all those things, whatever the function you require, that is going to be converted image, and then that can be implemented in any kind of platform. So that is the advancements today we got. So that is the thing that is discussed with that virtual machines. So now people are not using simple virtual machine. Now people are using this Docker containerization. Even with we have some issues, that one we have in IoT, that edge analytics and data analytics and all, and that the microservices people are using. Further, they have improvement in virtual memory. People are using some microservices. With that, they are using serverless computing. All those things now something upgradation in that technology. But somewhere still people are using that virtual memory along with the hypervisor, all those things. So due to some security issues, people are upgraded, as well as according to the requirement, the cost, people are using still that virtual machine. I won't say it is outdated, but some advancements are there in virtual machine also. Okay, so for that, the software that will be support, already you all know, virtual machine monitor as well as hypervisor is used. This monitor will help you to how to map the virtual resources to physical resources. So what is the purpose of VMM? Is nothing but it is used to map the virtual resources to the physical resources. It will be more useful in a multi-programming environment. So how we can protect the memory as well as IO devices. For that, people are using this one. So when the guest virtual machine runs the same ISO as the host, that is, we can use as a host as well as we can use some other operating system also. We can use that native hardware as well as bare metal. People are discussing about bare metal or something like that. It is going to be whether we can go with the native hardware or otherwise we can use bare metal or something like that. So if the IO intensive workload is also IO bound, what about IO? So we have discussed about the memory. What about the IO? That there will be some protection has to be done along with that IO. So for that also we are going to use some joint effort of architecture and an operating system in order to protect that input output. So you can think there will be something called as memory mapped as well as IO mapped IO. Why? Because memory mapped IO is nothing but we have some memory portion for some sort of instruction, some sort of instruction will be based on IO, input output. So, for example, input, output, some set of instructions will be used. But whenever we are think about memory, that size is going to be more. Whereas in case of I/O memory, that is going to be very minimum. Why? Because that I/O related device is going to be very minimum. That is going to be interface. So in that case, that memory is going to be 64K, maximum 64K. Now in latest i7 processor, that is going to be little bit higher memory according to our requirement people are using. But basically, if you refer to any basic architecture, that scale memory size is going to be 64 MB or otherwise 1 MB or something like that. Okay, but whenever we talk about main memory, that is going to be 1 TB or something like that. So to improve the performance of virtual machine, so we are going to reduce the cost of processor virtualization. While that there will be some steps has been taken by IBM mainframe hardware as well as virtual machine monitor to improve the performance. So where we can improve the performance means, so you all know there will be one issue, there will be inside that the 6-stage optimization, there will be the last step, how to avoid that translation. So we have to improve that performance. So increase the performance by increasing the speed, reducing the latency by converting that physical address, sorry, virtual address to physical address. There we can improve that performance of virtual machine, and then we can reduce the cost of that processor virtualization, and then we can reduce the interrupt overhead cost due to the virtualization. So interrupt, you all know. So there will be some migration is going to be there. So in that case, how we can reduce, what are the overhead related to migration? So how we can, that's why I told you now the people are using this Docker machines, Docker containerization for in order to reduce the overhead. And then we are going to reduce the interrupt cost by steering the interrupts to proper virtual machine without invoking VMM, all those things, without using hypervisor, how that invoking has been done, all those things. These are all the steps it will be taken by IBM for in order to reduce the overhead related to virtual machine. So you all, there will be one important issue related with coherency of cache data. So whether whether the data is going to be found in memory or cache, that you all know. I can store the data in memory. That program will take the data from main memory and then it will process. So if that frequently used data, if that data is going to be frequently used, it is going to be stored in the cache. That process you all know. So with a single processor, there is no problem related with stale copy. So you all know what is maybe a stale. So I am going to take the data. For example, that process in a multi-processing environment, the processor one will take data from a particular cache. Similarly, that is going to be taken by P1 as well as P3. So if that P3 gets the data and then it do some computation, and then according to that, it is going to be updated in that memory, but it is not replicated in that remaining processor core. So in that case, because the same memory is going to be shared in different processor core local caches, at that time there will be stale will occur. That is going to be stale. But if that processor is going to be, if you are going to use single processor, there won't be a problem with the stale copy. Whereas in that case of multi-processor and I/O, so we have some copies may be inconsistent. So that is that issue. Stale will be above. The processor may read wrong, or otherwise it is going to have the stale copy. That problem and all you all know. That is going to be called as cache coherency. So in that case, if it is going to be happen in I/O, so frequency of problem for a multiprocessor when compared with that I/O, so multiple data copies. So but it rare event, normally that it is going to be happen rarely event in avoid I/O to by whenever possible. So in that case, but program running on multiprocessor will want to have a copy, the same data in several caches. So in that case, we have to have some hardware mechanism just going to be used like snooping based or directory based, that will be helpful for in order to avoid such kind of issues. So now coming to that I/O coherency. So where does that I/O occur in a computer? So where we can cap that? So if you refer to the previous cache and all, that cache is between the input as well as output. Okay, so you all know that the cache is going to be between input side, or otherwise the catch will be in the output side. So that diagram, if you, I think you can refer to the previous slides. According to that, you can recall that one. So here also, whether I was an input output memory is also going to be that input and output is going to be that within that cache, or otherwise at the output side we are going to. So imagine replace that main memory with IO, that IO memory. That's all. So replace that main memory with IO. That is going to be that. So in that case, it interferes with the processor. So what are the problems? It will say whatever we are going to. For example, whatever we have faced during that main memory, that is going to be same for IO also. So here also we have to prevent the stale data problem. We have to avoid less interference, which means that the processor should process, that you all know, the process should not interfere with other. Even though we are going to have shared memory, shared resources, the process should not interfere. So in that case, that hardware as well as that operating system. I think we have discussed that one. So we have that architecture as well as that operating system will take care of. So our operating system, as we have that has to take care of all those things. Okay, so that has to be done here also. So what will be the solution? So here, what will be the solution? So instead of IO occurs directly to the main memory, we have to keep it in main memory without acting as an IO buffer. So whatever that updation has to be kept directly to that main memory. So what we have write-through cache. Normally write-through cache means you all know. So main memory would have to have data copy of the information. So no stale data issues for the output, only used at the first level. So whatever the write-through cache, whatever we are going to update, the same thing has to be updated in the main memory also. That is going to be called as write-through cache. Already you all know. So in that case, data caches will L2 cache using the write back cache. So whatever, so everywhere we have to update. So in that case, it requires extra work. So we need some extra work. What we means, so we have to copy everywhere. So in that case, it requires some extra work. So what will be the solution? So what will be the solution is there is no block of input power. What we have to do is we should not keep that input in the cache. So we have to keep all those whatever the necessary data. We have to. It should not be cached. So instead of that, we have to use not catchable. Everything has to be main memory. That there should be a data transfer always has to be between IO as well as cache. So we are going to avoid cache related operation for this IO related operation. Most probably, if you refer to any architecture, that input output whatever we are going to have, that will be always the data transfer between memory, main memory along with the input output. The OS can always input to such a page. So hardware solution is check the IO address as input to see if there is in cache or not. So first you have to check for, and then we have to try to avoid, and then we have to invalidate entries to avoid stale data. So in that case, we have to can be used for output with write back caches. So that is very important. So if extreme point, we have to use write back. So in that case, if it is, even though it is going to be cached, we have to update in that memory in order to avoid stale. So in that case, we are going to quickly review that cache. What happens whenever, I think I can skip, but still I want to just say some few points which are not covered. So whenever we are going to have a write hit, so whenever write hit occurs, so whenever we are going to have write through, where we are going to have two policies, write through, write back. So in that case, the write and both the block in the cache as well as block in the lower level memory, that you all know. So whereas in case of write back, the information is written only onto the block in the cache, not in that main memory. So the modified block cache is written to the main memory when it is replaced by another block. So for example, if a write back occurs, so if you want to update, in that case, that the block has to be replaced, and then we have to again I have to write back that modified block. So in that case only that updated information will be available only in write back policy. So since the data are not needed on a write, there are two options on write miss. Sometimes we should not need. For example, we are not no longer we are not going to use this same data. So in that case, what we are going to use, we are going to use something called as write allocate, or otherwise no write allocate. So this is that option. So this is case write allocate means that the block is allocated on a write miss followed a write hit action above. In natural option, write miss act like a read miss operation. So we are going to have read miss operation, then we have to update that. So in that case, in the lower no write allocate, we are not going to allocate a modified block should not be updated in the memory. That is a possibility. So we are not going to repeat that process. So now coming to the memory hierarchy in that ARM Cortex 8, 8, and then Intel I core sum. So what is ARM Core 8 is nothing but a customized version. So whatever, why? Because that ARM Cortex 8 and all, it is similar to your ARM 7 architecture, but we have something called as customized. What is mean by customized means whatever they required, whenever we required some options, so that alone we are going to keep it. According to the application, whatever the requirement, according to that it is customized, that it is going to be called as IP core, intellectual property core. But whatever the basic things are available in ARM 7 is also available in the Cortex 8 series also. But only thing is some customization has been done, which means that the memory requirement, IO, and then the peripheral, according to that requirement, connecting to the requirement of application, it is going to be called as application core. Or we can use that word called system on chip. So that system on chip. So for example, further it is not possible to upgrade, but you can use it for continuous operation, which means that continually it is going to be no longer it is going to be used for that particular specific operation. So in that case, it will have simpler memory system. So for example, if I want to review that, here they have reviewed that two-level cache hierarchy used. So here, for example, we all know there will be something called as main memory, there will be something called the CPU core. What exactly we are going to have is, whenever there is a data requirement, whenever the data is required, it is given to the CPU. But the register also, it will supply some data. Whereas in case of, whenever we need some repeated information, that is going to be cached into the level 1 cache. So that is going to be on chip. So in that case, that frequently required data, always it will be put it into the cache. So whenever that CPU requires some data, it will be taken from register, or otherwise the next option will be given to L1 cache, where it is in on chip. But if there is a cache miss occurs, what it will do, again it will go to the next level hierarchy. So in that case, it is going to be a unified cache. In that case, L2 will supply that information. Here also there is going to be the miss occurs. Again, what it will do, that processor, it will take the CPU core, it will take from L3 cache. So in that case, that will be supplied by L3. What happens here, if that speed is going to be, the latency is going to be more. So whenever we are going to move from L1 to L2, L2 to L3, there will be some latency will occur. So even though the size is going to be more, it will accommodate more, but the speed is going to be reduced. Okay, so that information you have to keep it in mind. So here, if I am going to take from register, within a second, nanosecond, I can get the data. Even if I'm going to take from L1 cache also, there will be some very minimum latency is going to be. But what happened here, what will be the problem here is the size is going to be very much. Whereas in case of the CPU, that is going to be external, so L2 is external. So in that case, it will take some time. But advantage is that size is compared to L1, that the size is going to be more. Whereas in case of L3, that it is far away from the CPU core. So in that case, the time will be more, but the size is going to, time will be latency will be high, but the size is going to be more. Similarly, that main memory. So these are all the things we have to look forward whenever we are going to discuss about caching. So what are the 6 basic optimization techniques we have? I think these 6 basic optimization techniques, you all know what will be the larger block size. So larger block size, you all know. So we have a maximum block size means we can go with more number of words. Okay, so in that case, I can miss. Or otherwise, I will have bigger caches. So we have bigger caches means I can keep more number of blocks. So in that case also, we will call it as n block associative, and then set associative, 2 associative, all those things. So whether we have one single set, or otherwise we have 2 set or something like that. So with that case, higher associative, we are going to have reduced miss rate, multi catches, all those things. But only thing is, we are going to think about the last one, avoiding address translation during indexing of the catch to reduce the hit time. So we are going to take this particular point, avoiding address translation. So we are going to reduce the translation time for in order to reduce the hit time. Okay. So in that case, how we are avoiding the address translation during indexing of the catch to reduce the hit time? So in that case, what we are going to do is that CPU uses the virtual address that map to a physical address. So already you all know that the virtual address is going to be mapped to a physical address. Um, that is option. In that case, the catch may be either use virtual address or physical address. So to get the best, so if I want to get the best, both virtual address as well as virtual cache. So for that, if I want to convert that into physical address, we need some thing called as use that page offset, as well as we are going to have that index to catch all those things. We all know that we have something called a tag. With the help of the tag and then offset, I can calculate the physical address. That and all you all know. So that thing you can might have seen that the previous lecture what we have discussed in that how protection of memory. At that time we have discussed all those things. So now we are going to see how virtually index a physical tag. So in that case, you all know the cache contains 64 bytes of data in 64 byte blocks. So we have, for example, the size of the cache is going to be 64. So in that case, 64 blocks can be there. So either we can follow two array associative placement, or otherwise we can use least recently used replacement. So whatever we are going to either we can go for two-way set associate placement. So two-way associate, in that case, we have two sets of information. Or otherwise, we can whatever that recently used, that is going to be replaced. So instead of keeping all those things, we are going to use recently used replacement. We have something called as write back, or otherwise we can go by write allocate on a write miss transaction. Whenever we are going to have write miss, we can write back all those things. So in that case, what is going to be the limitation? The limitation is nothing but we have a direct map, no longer the bigger size. So we go for virtual pay two-way associative. So in that case, we can use 9 plus 6 bytes or in 32 KB information. So these things we are going to see. For example, we are going to use portion of index must be translated from virtual to physical address. So in the index alone are going to be translated from virtual to physical address. So that's how it is going to happen. We are going to see. So for example, this is going to be the overall diagram. So we have something called as tag. So that is going to be the size. We have the tag size is going to be 25, and then we are going to have 9 index is going to be 9. We are going to see how that 9 and all we are going to have. That is going to be called as how to calculate the index. We are going to see, and then we are going to have something called as block offset. That is going to be 6. So whenever there is a valid, so we are going to have valid data. If it is available along with the data, we are going to check with that catch one. If it is not available, again we have to go to the next block, and then we are going to get the data. So similarly, we are going to get the data from the CPU address. So this is possibility. So either I can take from for example, catch, or otherwise I will take from the main memory. With the help of this multiplexer, I will get the victim block for in order to get the data from the lower memory. So this is the overall arrangements. So for how it is going to be call it, how this diagram is, we are going to give the detailed theory about this particular diagram. So for Optron data cache, so there will be something called as Optron data cache, which in that case, for example, first you have to remember 48 virtual address to the cache for tag comparison. So we are going to have 48-bit virtual address to the cache for tag comparison, which simultaneously translate into physical address. So that 48-bit virtual address is going to be converted as a 40-bit physical address. So we are going to consider 40-bit. So in that case, that physical address is divided into 2 fields. This 40-bit physical is divided into 2 fields. So in that case, 34-bit block address and the 6-bit block offset. So previously I told you, so we have tag as well as index. So in that case, this 34-bit and then 64-bit block offset. So that is going to be there. So 34-bit plus 60, that will give you 40-bit physical address. What will be the step one? So the block address is further divided into an address. So block address, this 34-bit is divided into address tag as well as cache index. So here the block address is divided into 25 plus 9, 36. That is going to be divided into tag as well as index. That is the information it is given. So if you read this theory, it will be more helpful for the previous. So I couldn't put all those things in a single slide, and that is why I have given in this one. So what will be the step one? The block address divided into tag as well as cache index. That cache index, what is the use of the cache index? That will select the tag to be tested if the desired block is available in that. With the help of the tag, already you all know that tag is going to get the tag will get the address, and then with the help of the address, we are going to check for whether this particular address is available in the cache or not. With the help of cache tag only, we can check for whether this particular memory is available within this cache or not. So in that case, this set associative is set to 2, and we calculate the index. How we are going to calculate the address? We are going to see. Okay, so for example, with the help of there will be some formula it is given. You can refer in that book. So that how that 52 MB of cache is going to be calculated in that formula. It is the direct relationship it is given. So based on that, we are going to calculate that index. So hence that index is 9, going to be 9. So how it is going to be calculated is not. I have not given this particular slide because I missed it. So it is referred in that book. So how to calculate the cache index? That cache index is 9. Okay. So in that case, based on that, we are going to get. So so we have to minus 34 minus 9. So we are straight away. It is not possible to use the 64-byte. We have maximum. We can use 8 bits. So 8 bytes. So in that case, so with the help of 25 bits wired, we are going to calculate that offset as well as index. So with the help of this 25 bits as well as that tag address. So previously I told you this offset 6. So in the 25 as well as 6 is going to be there. So that is going to be get that appropriate bytes or 8 bytes of information. So after reading the 2 tags from the cache, we are going to compare. So whether this block is available or not. If it is block is available, that is going to be matched. So that is why finally we are going to load the proper data into the cache from the 2:1 multiplexer. That is the steps. Okay. So if you refer to that operation of operand data in TLB during translation, so here also we are going to use the translation lookup buffer. So you all know this is that why TLB is used. You all know that is going to be little bit speed. So that will whatever the recently used is going to be in the TLB. So previously we have discussed about is we have some amount of blocks which is going to be there. Within that we are going to get the that particular portion alone is going to be converted into virtual address to whereas in case of physical address. Whereas in case of translation lookup buffer, which means that it is little bit improved performance. So which means that which and all recently required, recently repeatedly used, in that alone we are going to put it into the TLB. So in that case, so here what are the steps to be followed for in order to convert that into physical address translation. So in that step 1 and step 2 to set the virtual address to all the tags. We are, for example, the step 1. So the whatever the tag is going to be valid, allowed to match. At the same time, the memory access is checked for violation against protection information in the TLB. So for example, there should not be any violation, which means that only repeated information alone, repeated block alone we need. That is why we are going to check for violation and then read write, whether it is going to be a user or supervisory mode, and then whether we have a data address tag, all those things are given. So we reference whether it is a valid or read write, user or supervisory mode, whether we have a data and then we have address, we have some tag and then physical address. So in that case, we are going to map. So here we have, instead of this one, we are going to have 40:1 multiplexer. So in that case, we are going to get higher order 28 bit. So inside in that 40, we are going to get only the higher order 28 bits of address. The lower order will be taken from this. For example, 20-bit physical address, 40-bit physical address. So combinedly, we are this lower 12 lower order will be taken from this physical address. So we are going to combine this one. Based on that, we are going to get the 40-bit physical address. So this is that address translation which is going to be done for TLB. The same thing here we are given how that it got translated into physical. So we have a 64-bit translated address, that page number 50, and then we are going to have the page offset 14. So that is going to be previously what we have done. So that TLB tag address as well as the TLB index, that is going to be calculated. Based on that, we are going to compare with that L1 catch. If it is not available, again we have to go back to the next. We have to go to the next catch, and then we have to compare. If it is not available, further I have to move to the next level. So based on that, finally we have to take from the main level. So these are all the ways for in order to get the data from the catch from different levels of hierarchy. Okay. So this is going to be the end of your I think unit 4. I think almost we have covered. Okay. So just theory, just this is one theory we have in this particular portion. So unit 4, if you refer to that previous question, not previous question, most of the time there will be some question in that 10 optimization techniques as well as memory protection, memory hierarchy optimization, and then all those things. Okay. So, but this portion, at least if you have to know how internally that wedge translation is going to be done, that you have to answer. Okay. Sometimes in the 2 mark, this how that index is going to be calculated. That formula I have not mentioned here. It is given in the book. You just refer to that particular thing. You can get that. Okay. So that is going to be the end. Today I will complete that. Complete